All right, so let's get started here. So last time we wrapped up our discussion of molecular structures. That was a particularly long topic to cover. To finish off this particular unit, we're going to cover a relatively small topic, and that is the discussion of gases in chemistry. All right, remember we said that all matter can be broken down into three phases: solids, liquids, and gases. All right? And it turns out that gases are the easiest of the three to describe because with gases, neighboring gas particles are really far apart from one another. So they're not interacting with one another. It turns out that these interactions that take place between neighboring molecules are really complicated. They're really hard to explain. So liquids and solids, where these molecules are really close together with one another, interacting strongly with one another, those properties are a little bit more difficult to explain. Gases are very easy because everything's really spread out. There isn't this intramolecular interactions that we have to worry about with gases. All right, so they're a good starting point when we're discussing our states of matter. Again, we're going to focus on gases, and there are going to be four variables that we're going to be relating for our gases here. And these are all intimately tied together, we're going to see. All right? So the first, we use the symbol N for number of moles. All right, so we're going to relate the number of moles of gas molecules to V, the volume of the gas. All right, so the amount of gas particles and the volume of that gas are very closely related to one another. All right, this is also going to depend on the temperature of the gas. All right, but there's one important caveat that we have to make note of with temperature in this particular chapter. All right, we're going to say we must be in units of Kelvin. All right, so when we're talking about gases and we're relating these variables to one another here, it's really important that we convert our gas to units of Kelvin as opposed to what is the more commonly used unit in the lab, degrees Celsius. All right. We find Celsius to be really convenient in part because we have like an intuitive sense of it, but from like a fundamental theory, ground up theory kind of perspective, Kelvin is the fundamental unit for temperature used in science. All right, and there's an important reason for that. So why do we use Kelvin? Okay, so importantly, the temperature of a substance, whether it's solid, liquid, or gas, is proportional to the kinetic energy in your sample. All right, and kinetic energy is something that you would have talked about in a physics class. Simply speaking, it's the energy that something has because it's moving around. Okay, so temperature is proportional to kinetic energy, which for gases is simply the speed at which gas molecules are moving around. All right, so gas molecules are here. They're bumping around this container here. They're traveling. Each one's traveling in a random direction, just kind of moving around in this container. If we take this container and heat it up, what we're doing is we're increasing the speed at which all those gas particles are moving around in this container. So they just go faster and faster and faster as we increase our temperature. All right, so then why do we have to be in units of Kelvin? Simply speaking, it is because of this concept of absolute zero. All right, 0 degrees Celsius is pretty arbitrarily defined. It's defined at the temperature at which water freezes. Okay, but 0 degrees Kelvin is a very special number. It is the coldest temperature that you could possibly get to. There's no way that you're going to get to a lower temperature than 0 degrees Celsius. And the reason for that is at absolute zero, T equals 0 degrees Kelvin. Again, what we call absolute zero. There is no motion of particles. Right? So your temperature is supposed to be proportional to kinetic energy. That means if you have 0 kinetic energy, you should be at a temperature of 0. And that is what the Kelvin scale is. All right? So it's got this minimum, this 0 point. And that's really important because 0 degrees Kelvin, 0 temperature should equal 0 motion of your particles. Right? No more kinetic energy. The theory just doesn't really work if you use degrees Celsius. You would always have to convert to Kelvin first. All right, so we look on our constants page. We didn't do any math really last chapter. We're going to bring back the math here this chapter. All right, if we look, we have our conversion for Kelvin here, where Kelvin is equal to degrees Celsius plus 273.15. All right, this magic number, 273.15. We take our temperature in degrees Celsius, we add 273.15. That's our temperature in Kelvin. What's a pain in the butt, or we want to make note of about this conversion here, is that it is different from every other unit conversion on this table, in that it's not multiplication and division, but it's addition or subtraction. And we have different rules for our addition, subtraction, sig figs. So before we move on, let's just do one temperature conversion where we want to convert from 22.5 degrees Celsius into Kelvin. All right, and what our constants page told us is that Kelvin is equal to degrees Celsius plus 273.15. And it had these little asterisks next to it, meaning that 273.15 is an exact number. It's not going to limit our sig figs. So when I do my unit conversion here, since it's addition, it's not about counting. It's about the position of my sig figs. So I got to line these up at the decimal. My 22.5 plus the 273.15. All right, we're going to mark our last digit, our last sig fig in each one of these numbers. So for 22.5, I'm going to mark that 10th place right there. Okay, but for my magical 273.15 number, this is exact. So it has an infinite number of sig figs. So I can tell just based on the position of this first number here, my sig figs for my temperature are going to be in this 10ths column here. So when I do my math, 22.5 plus the 273.15, punch it into my calculator, I get 295.65, and I know I'm going to have to round to that 10ths place. So 273.7 Kelvin. Yep. Wait. 295. Oh my gosh. My bad. Got 273 on the brain. 295.7. All right, and again, we have different rules for addition and subtraction. So notice that my temperature started out with 3 sig figs. And when I converted to Kelvin, I have 4 sig figs. Again, that's because it's not a counting rule. We got different rules for addition and subtraction. We can gain a sig fig, and we will routinely in these conversions here. All right, so when we have it's very natural to go into the lab and to use your thermometer that measures in degrees Celsius. But if we're going to be using this equation that we're going to be introducing here, if we're talking about gases, anytime we're talking about gases, we need to convert our temperature into Kelvin. All right, so I said 4 variables. We got one more here. These first 3, you could use to describe a solid, a liquid, or a gas. A solid has a number of moles of particles and a volume and a temperature. A liquid has a number of moles of particles, a temperature, and a volume. All right, this last one, though, is unique to gases, and that is this concept of pressure. Solids, liquids, do not have pressures associated with them. Only gases do. Okay, so then what is a pressure? All right, so pressure is a measure of the force imparted on the walls of a vessel by gas particles. Okay, so what the heck does that mean? So gases are all traveling around randomly, right? All of these things are spread out. In this picture here, it looks like they're frozen. Of course, that's not the case. Everything's in motion. So this molecule over here is going in this direction. This molecule over here in this direction. This one and this one, right? They're all traveling around randomly in space. Well, every one of them will eventually go and hit the walls of this container here. And in doing so, they will impart a force on the walls of that container. There's this expansion force that they're doing. They're all trying to get out, trying to expand out here. And so this force that's imparted on the walls of the vessel, this is what we call pressure. So our force imparted on our walls, that's what we call the pressure of the gas. All right, so the higher the pressure, the more those gas molecules are banging up against that side of that container. All right? If you've ever seen like a tank of helium or something that's used to fill up a balloon, it's made of these ridiculously thick steel canisters. The walls of those canisters are really thick. Those canisters are ridiculously heavy. And they're not heavy because of the gas inside. They're heavy because those containers have to be really strong, because gas molecules are slamming into the walls of them really hard, because they're under a really high pressure. All right? So these four variables here, the number of moles of a gas, the volume of the gas, the temperature of the gas, and the pressure of a gas, these are all intimately related to one another here. Okay? So before we go on and see how they're related, let's talk a little bit about pressure and specifically about the units of pressure that we use. Okay? Pressure is kind of an annoying thing because it is very relevant in a bunch of different fields. It's very relevant in chemistry, but also a lot of different engineering fields. And just to be a pain in the butt, everybody has a different preference for units that they use. All right? So like the chemists in chemistry, typically speaking, you will see things in either what's called torr or ATM. All right, but there's some others. The physicists, for no good reason, they like pascals. And the engineers, if you go and you check your tire pressure, it's in PSI. So there's all these different units that we use for pressure. All right, but just like any other set of units, we can jump between them fairly easily as long as we know our unit conversions, and we have a whole section on our constants page dedicated to pressure units. All right, so let's just practice one of these unit conversions. It's been a minute here. Unlike temperature, these are multiplication and division, so our sig fig rules aren't too bad. All right, but we want to convert, let's say, 2.5 ATM into units of torr. All right, so 2.5 ATM into torr. Let's go to our constants page. Again, if we look right above that temperature section, we have this pressure section here. All right, so again, everybody take a second and convert 2.5 ATM into torr, doing one of our unit conversions. So I'm going to use my fact that 1 ATM is 760 torr. Right? I can build my unit conversion where I stack one side on the other. Or I can take it and flip it around. Okay, so then starting my conversion, I'm going to use my 2.5 ATM. I'm going to multiply by my conversion factor that allows ATMs to be canceled out. I punch that into my calculator. I get 1900. If I go back and do my sig figs, my initial pressure has 2 sig figs, and what about that 760? It's exact. So I'm just going to make sure to report my answer to 2 sig figs. As long as I don't put a decimal back here, 1900 as written has 2 sig figs. Remember, you do not want to say 19 because these are very different numbers. Don't chop off those zeros at the end. Can't change the number, we're just rounding it. And my units would be torr. All right, so just like all of our other units here, we can convert between these different units of pressure given our constants page, just like we converted between inches and centimeters. All right, so these 4 variables here are related by what's called the ideal gas law. All right, so this is an equation that relates those 4 variables together. The ideal gas law makes 2 really important assumptions about your gases, that they are ideal. These are these ideal conditions. An ideal gas has 2 very important properties. One, it does not interact with neighboring gas molecules. All right, and as we said, that is a very good assumption that you can make about gases because the distance between neighboring gas molecules is really far in the gas phase. They're not interacting very strongly with one another. Right? So this is a good assumption because our gas molecules are far apart. The other assumption that we make that makes a gas a quote-unquote ideal gas is that the gas particle has 0 volume. That gas molecule itself is not taking up any volume. And that's of course not true, strictly speaking. Again, these are assumptions that we're making. But it's a pretty good assumption because gas molecules are really, really frickin' teeny tiny, right? Just like all molecules. We're talking about something that is insanely, insanely small. So it can be well approximated as just being 0 volume. So again, a good assumption because molecules are so teeny tiny small. All right. So the ideal gas theory is studied in every single general chemistry course here. One, because again, it describes the behavior of gases. And we got these two assumptions here that seem like they're not quite true. And they're not like 100% true, but they are good assumptions. All right, but it's got one big win historically, which is why we continue to study it to this day. This theory was first proposed by scientists in the late 1700s, early 1800s. A ridiculously, ridiculously long time ago. All right? Some of the very earliest work that was done in chemistry was building this theory here, right? When they were still getting their hands around the fact that the world was made up of atoms to begin with. And then, 200 years later, the big brains in the computational department, what's called statistical mechanics, the scientists that just work on whiteboards all day long doing math, they came up with the exact same theory. And that just never happens, that the two meet, that the experimentalists back in the day, that we don't complicate things over here in the future. No, no, no. It turns out that what they discovered back in the day was a really, really good theory. So we sort of take this to be the ideal gas law. It gets bumped up from being just a theory to a law now, which is like a special class of theories in chemistry. All right, because again, it's just kind of stood the test of time. And again, this is going to be an equation that relates those 4 variables. Our ideal gas law, and we just want to memorize this. We're going to chant it over and over and over again, is PV equals nRT. All right, and this is one we just got to know, the ideal gas law. PV equals nRT. Okay, P is again the pressure of the gas, V the volume, N is the number of moles. All right, I'm going to skip over R for right now. Our last variable is T, the temperature of the gas. And what are we going to note about that temperature when we're using our ideal gas law? It's got to be in Kelvin. Your units of pressure, you can use any units of pressure. You can use any units of volume. All right? But your temperature has to be in units of Kelvin for this ideal gas law to work. All right, so then the R here, what's this missing thing? This isn't actually a variable in this equation. It is what's called the ideal gas constant. All right, so it is just a number that goes into this equation here. All right, the only thing that this ideal gas constant depends on is the units that you use for pressure or volume. Okay, so this is just a number. It's not a number that we have to have memorized or anything like that. It is another addition to our constants page. One of these values that's up here next to Avogadro's number. That very first line there is our ideal gas constant. All right, and we can actually kind of ignore this bottom one here. That's for future courses. All right, but our ideal gas constant is equal to either the 8.082058 or 62.36. And what are the difference between these units, between these values for our ideal gas constant here? Why are they different numbers? Because one has pressure units of ATM, the other has pressure units of torr. And you could convert between the two. I gave you them both here, but I would only really need to give you one. You could always convert from ATM to torr for your ideal gas constant, right? That's the only difference between these numbers. All right, so let's use our ideal gas constant. We'll use units of ATM for our pressure. That's kind of a default for chemistry, especially modern chemistry. All right, the 0.082058 liters ATM mole Kelvin. And these units look really awful and scary here, but we're going to see why this is important. All right, so let's do an example problem here. All right, we're going to use our PV equals nRT. What is the volume in liters occupied by 2.6 moles of helium at 1.5 ATM and a temperature of 255 Kelvin. All right, so this would be a problem that utilizes our ideal gas law in a very straightforward way here. If we look at what we're given in the problem and what we're being asked for, what we're being asked for here is the volume in liters. All right, what do I always have in my ideal gas law? There's one of these letters up here that I can always find the value for. That ideal gas constant, right? I'll just look that up on my constants page. No matter what, we always have R. All right, if we look what else we have, we're saying that the gas contains 2.6 moles of helium. So which one of my variables do I have up there? If I have moles of helium, N, I have that this is at 1.5 ATM. So what does that correspond to? The pressure of the gas. And then lastly, I have a temperature. I was even nice and gave it to us in Kelvin here to save a little bit of time. All right, so I have 4 of my 5 terms in this problem here. I'm just missing one of these variables. And again, you'll always have R. So that's the name of the game. If you're given 3 out of the 4 variables, you should always be able to find that 4th one. Okay? And what we're going to need to do is just some very simple algebra here. Let's take our PV equals nRT, and we're going to rearrange this to solve for V. All right, solve for V. And by solve for V, I mean get V all by itself and move everything else to the other side of the equal sign. Okay, so if I divide both sides by pressure, I'll have volume equals nRT over P. And again, I got everything to plug in on the right-hand side of this equation here. My 2.6, and I'm going to be good with my units here, 2.6 moles. My value for R was the 0.082058. Liter ATM per mole Kelvin. My temperature is that 255 Kelvin. And I'm going to divide by that pressure of 1.5 ATM. All right, so I'm just plugging in my missing variables here. N is my number of moles. R is that value from the constants page that I always have. T is my temperature. I messed up my colors. T is my temperature in Kelvin divided by that pressure. Okay, so I'm going to punch this into my calculator. I get my volume equals 36.26963. All right, let's look at units real quick. Let me get rid of some of these colorings here so we can see a little bit more clearly. R had that big, ugly mixed units. All right, and what we're going to see is that's because that's going to square away all these different quantities from our ideal gas law. I have mole on top divided by mole from my ideal gas constant. I have Kelvin divided by Kelvin from my ideal gas constant. And lastly, ATM divided by ATM. So now I'm left with units of liters, right? So all of these different variables have different units associated with them. So that's what R is doing there, is help us square away all these different units, leaving us with the units that we want, units of volume. All right, and it's been a minute since we've done some math in this course, but what's the last step that we always got to do? Sig figs. Okay. Now, there's a lot of terms here, but fortunately, this is just a multiplication division problem. So all we got to do is go through and count our sig figs in everything and make sure that our final answer is reported to the minimum number of sig figs. So my moles and my pressure have 2. An ideal gas constant is not an exact number, but we do have a value with a lot of different sig figs here. 1, 2, 3, 4, 5 sig figs. And then my temperature has 3. So then how many should be in my final answer? Yeah, the minimum here, which is that 2 from either my pressure or my moles, is going to limit me. Okay, so this gas would occupy a volume of 36 liters, reported to the correct number of sig figs. All right, so our ideal gas law, this equation here, it relates these 4 variables and this constant R. We always got our constant R. So as long as we have 3 of the other 4 variables, we can always find that one missing term. All right, so let's do one more. I'm going to have you all do this one on your own here. Okay, we can just make note our value of R from our constants page. Okay. All right, what is the temperature of the gas if 6.3 moles of that gas occupies 14.65 liters at a pressure of 10.3 atm? Again, we'll be using our ideal gas law. All right, so what is it that I'm trying to solve for here in my ideal gas law? My temperature. I always have R. I'm given the volume, the number of moles, and the pressure in the problem. The only thing I'm missing is my temperature, so I can rearrange to solve. T equals PV over RT, or over NR rather. So then I plug in here. My pressure is 10.3 ATM, 14.65 liters. Divided by that 6.3 moles, and that ideal gas constant. And we'll put in all these units here to be good so we can see everything canceling out. All right, so punch this into my calculator. I get my temperature is equal to 291.88607. I'm going to look at my units here. My ATM cancels out. My liters cancel out. My moles cancel out. And I'm left with 1 over Kelvin, which is the same thing as Kelvin. All right, so again, those temperature units for my ideal gas law are units of Kelvin. How many sig figs am I going to report my final answer to? So I got to go back and look at everything, right? So my 10.3 has 3. My volume has 4. But my number of moles only has 2, and that's what's going to limit me. So my final answer here would be my temperature is equal to 290 Kelvin. Right? Not 29, we can't forget that last 0, but 290. Okay. All right, so now we're going to learn another way to use this ideal gas law. This is what is called the alternative gas laws. All right, I like to think of them more as before and after type problems. All right, we're going to take a gas and we're going to change these conditions here. Okay, so importantly, this is all of these alternative gas laws are going to kind of stem from the same thing with our ideal gas law, PV equals nRT. Everybody, let's take this and solve for R, for our ideal gas constant. So what we get is PV over NT is equal to that ideal gas constant. And what's important to understand about this relationship when it's written like this is that this is a constant, which means whatever your gas is, whatever your conditions of your gas is, the pressure times the volume divided by the number of moles divided by the temperature always has to equal that same number. So it doesn't matter what your conditions are. You take P times V divided by NT, you always have to get the same number out of it. All right, so let's take a look at one of our alternative gas law problems, and we'll see how to use this here. All right, so we'll take a party balloon. Is filled with 1.5 moles of helium to a volume of 23.6 liters. What is the volume if a total of 2.8 moles of helium is added? All right, so these are before and after type problems because I'm telling you that before this change was made, I had these 1.5 moles of helium in my balloon, and the volume was 23.6 liters. And then after this change was made, I'm telling you how many moles of helium it is, and I'm asking you for the volume. All right, so what's important is that both before and after this change was made, this has to be true. The pressure times the volume divided by N divided by T. They always have to equal that same number, R. So I'm going to mark for my befores here, my pressure before. I'm going to call this P1, V1, N1, and T1. My pressure, my volume, my number of moles, and my temperature before this change was made is equal to that constant R, which has to equal the pressure volume divided by N divided by T after the change was made. So I'm going to call this P2, V2, N2, and T2. Okay, and again, these have to equal one another because they have to equal that same constant R. All right, so then let's just simplify this and drop that middle R. We got P1, V1 divided by N1 divided by T1 equals P2, V2 divided by N2 divided by T2. Okay. So let's look carefully at what we have in our problem here. The 1.5 moles of helium, what variable is that in my problem? N, but specifically N1, right? The number of moles before this change was made. And the volume, V1, is also given to me. And I'm given my number of moles after this change was made, and I'm being asked for the volume. All right, so that means that my pressure and my temperature are not changing. So P1 equals P2. And T1 equals T2, right? No change. So if P1 equals P2, what can I do to my equation here? I get to simplify it. These will cross out. They're equal to one another. If my temperatures are equal to one another, they're going to cross out. So what I'm left with is just this relationship, V1 over N1 equals V2 over N2. And now I can plug in here. I'm given my 1.5, let me just zoom out. My 1.5 moles, my 23.6 liters. This equals this V2, I don't know, divided by my 2.8 moles. And now I can just cross multiply and solve for V2. All right, so if I multiply both sides by that 2.8 moles, it'll cancel out over here. And so my final answer, my B2, is equal to 44, rounded to the correct number of sig figs, I should have 2 liters. All right, so starting out with our before and after relationship, we got to figure out what's not being changed, what's being held constant, and that'll leave us with this alternative gas law relationship that we can use to solve our problem. We'll start off with another example of these alternative gas laws next time.